It's actually it's a continuum what I was talking about, and it's also a little bit what the everyone else were talking about. Thomas started with his thermodynamics and modeling and so on, and then there were experimental things that followed up, trying to somehow understand the fluid chemistry. But I'm going to revisit this a little bit again, and continuing with the supercritical or super hot or superheated steam, whatever you like to call this, to revisit the chemical composition of such fluids. And the thing is, in many respects, when we talk about supercritical or super hot, when we are referring to geothermal systems, we are really referring often to upper crustal conditions, relatively low pressure, and rather than conventional supercritical fluids that are maybe more commonly associated with metamorphic reactions and so on, even though the two, of course, overlap. But to identify the composition or understand the chemical composition and be able to forecast changes up in temperature and pressure and so on, this is a very important thing in order to identify supercritical fluids, like I was talking about before, how to possibly utilize such fluids, and many other things. And in the past, I mean, in the geothermal industry and science and engineering, I mean, we have studied things like this in conventional geothermal liquids by modeling and experimentally and studying active and fossil volcanic and geothermal systems, and many of these fossil one we call ore deposits, like Isabella was talking about before. But I want to turn back to this geochemical modeling part, and kind of Thomas started this explanation, is that in order to do a lot of these basic geochemical calculations that we are used to do for liquid-like fluids, well, if we move to the superheated conditions or these low pressure or low density super hot or supercritical fluids, we are often lacking, or completely often lacking, the thermodynamic data to parameterize such models, and we are also just lacking the basic thermodynamic model. I'm not going to go into this. I think Thomas made a wonderful explanation on where this is slowly going, maybe. But in order to be able to carry out such modeling, we need to have the input data. And of course, we can try to calculate this in some cases based on physical chemical principles like molecular dynamics or ab initio calculations, but we can also try to do some experimental measurements. And this is kind of what we have been doing. So when we look at supercritical fluid chemical compositions for those systems, the geothermal systems, and I'm focusing on them maybe here more than the ore deposit environments, even though they give equally much input into how these systems look like, is that where we have somehow encountered supercritical temperatures in these active geothermal systems, we have seen that the fluid composition is very variable. In many cases, like the ITTP1 case in the Krapla that we have heard about, and also at geysers in the US, where supercritical temperatures have been encountered, and Menengai in Kenya as well. The fluid seems to be purely water dominated. In other places, we have some volatile inputs, mainly CO2, like in Larterello and Los Humeros in Mexico. So it's maybe more of a water CO2 fluid. And then we have more complex brines. So Kakonta in Japan, that was the first deep borehole. This is really like a sodium chloride dominated brine. And then at the ITTP2 site in Iceland, at the bottom of the borehole, I mean, there were no fluids, so many of these are based on fluid inclusions, like in ITTP2. And you have a very complex concentrated brine. You don't even have a simple water sodium chloride. The ITTP2 brine is more like a water iron chloride and potassium chloride with some additional sodium chloride. So there is definitely a range of fluids and environment that we need to be able to model, independent of if we are able to do that. But if we start with the water-dominated fluids, these are often just approaching pure water, 99% water. And there seems to be, based on isotope-constrained water isotopes, to be of just a hydrothermal groundwater origin. It's basically just the thing I was talking about before. It's just heating up of the surrounding thermal groundwater to superheated to supercritical conditions. And this is maybe an interesting fluid to utilize directly, because we are utilizing kind of pure water. We don't have brine or a complex gas, which may be complicate the engineering part of utilization. And here we are starting somehow with our thermodynamic modeling. We are starting with the fluid type of almost pure water, okay, where we have some minor solutes plus water as a solvent. Then we have, of course, the brines. They can be up to 60–70%, maybe more percent water, and the rest is a salt. So it's very concentrated. These are maybe very difficult to utilize and haven't been extracted directly in boreholes for such purpose. But today it's kind of out of our reach to model this at the moment, at least in case of a multi-component modeling, because we are often even missing the solvent thermodynamic behavior. If we have, for example, a complex fluid like we had at the ITTP2, that was not pure water and a salt, but or a sodium chloride salt. It was more like a mixed iron chloride, potassium chloride, sodium chloride. It's kind of a difficult phase behavior. We are missing an activity model. We are missing solute speciation in such brines and so on. So what I'm going to talk about here is more associated with this former case where we have almost pure water and minor solids in that fluid. And as Thomas was talking about before, is that existing thermodynamic models and their parameterization, they apply, for example, the widely used HKF formulation. They apply to compressed liquids in a way, and do not somehow apply to the expanded superheated or low density supercritical fluids. So the HKF here is shown, as you have seen before in Thomas's talk. It's this white area. This is where we can use the thermodynamic model to calculate you can say chemical reactions and speciation and so on. And this is commonly done together with a simplified Deepak-Haskell activity model, for example. But when we increase the temperature at a relatively low pressure, if we are somewhere down here, for example, there is no model. And the relevant components, for example, that we like to model in these systems, they are just basic elements like hydrogen and oxygen, water, sodium, potassium, calcium, magnesium, chlorine, aluminium, sulfur, carbon, and so on. So where do we stand in a way? Well, we don't have really a thermodynamic model, and in a way we don't even have the measurements that we need to put into such a model to parameterize the model. So the other part that we are doing as a part of the GeoPro project that Thomas was talking about previously is that we are just starting to climb the mountain in this yellow region, so to speak, to just carry out experimental work on simple systems to obtain the basic thermodynamic data. And the start of this, that what we are doing is carrying out simplified solubility experiment of simple chlorides and oxides and carbonates and sulfates and things like this, rather than a complex data. And when you start looking around the literature, you realize that this area of temperature and pressure, this high temperature, low pressure, or this below 0.35 grams per cubic centimeter density, it's like a thermodynamic data desert. There is nothing there. There are some experiments on sodium chloride. There is something on sodium sulfate, but that's about it. And part of this is that it's a tricky thing to do experimentally. So one of the things that we have been doing is to develop another way of carrying out such experiments, and it's called a U-tube reactor. It's a little bit different from a normal autoclave. It's more like a tube or reaction tube. You can see it here, and it has a very funny shape. I don't want to go through that. It actually goes through a furnace, and then it has a funny shape. This U-tube, that's where the name comes from, because these experiments are kind of an open type thermodynamic experiments where the fluid is flowing through the solid that is within the reactor. And then we are playing with fluid dynamics as well, because you have to basically heat up the system to supercritical conditions before it hits the solid. And then at the end, there is kind of a quenching and sampling device. So we are moving forward quite rapidly, measuring everything that we can imagine in terms of a simplified chemical composition to provide new data to allow the parameterization of these thermodynamic models that Thomas was talking about before. The systems that we are looking at today, they are just here. They sound very basic, but many of these reactions that we are seeing in these systems are actually quite basic. So we have already started the experiments that are bold here with the chlorides. It's basically going down the entire column from lithium to cesium, and then calcium and magnesium, and possibly adding strontium chloride. It's also involving all kinds of hydroxides, carbonates, sulfates, and then simple oxides. So we are kind of done with this part here, and we are moving towards the oxides here. And this is how it looks like. It's just a simple experiment of solid solubility in this superheated vapor or supercritical fluid from 350 degrees to 700 degrees at pressures from 25 bars to maybe up to, in some cases, 300 bars. And we are maybe mostly focusing on this part here, and then slowly we are approaching this liquid-like behavior. And then these data points can be fitted against a thermodynamic model to obtain the thermodynamic values or parameters in order to carry out some models. This fitting process is of course going slowly, because there is not a lot of data to fit anything against, and we are kind of starting our journey. But initially we are obtaining equilibrium constants for given reactions, or delta Gibbs energy of reactions, and then formation and evolved things. Assuming a very simplified chemical model of a neutral species, it's basically ignoring ionization reactions to start with ligands and hydration with the water, and assuming ideal behavior, where the activity is basically just the mole fraction of the solute in the solvent. And then we are fitting this towards some kind of temperature, pressure, volume, or actually a density function like Thomas was talking about, at least to start with, because density makes a lot of this nonlinear behavior like you're seeing here below into a more linear behavior. Here we have plotted the solubility as a function of the log density. Of course, I mean, this fitting will eventually maybe be revisited in terms of parameterization of a fully developed thermodynamic model that can be applied under these conditions. But we are moving forward with some simplified, at least today, log K function or log K density functions that can be used to carry out some modeling. And this is what we are then doing already. We are trying to implement the solubilities that we are already doing to calculate or estimate or model presumably the composition of a simplified supercritical water-dominated fluid. And I'm going to show you how we are doing this modeling because it crosses the boundaries of these thermodynamic equations from a liquid-like system, like we were talking about the HKF, towards this expanded superheated to supercritical fluid where we are obtaining the new experimental data to carry out some of this basic modeling. So basically what we're doing is that we are starting from somewhere here in a liquid, and then we are heating it up, well, in the model, either through the two-phase field of liquid and vapor or above the critical point. This would be just kind of an expansion without a phase transition. And then into this super hot or supercritical region here at these low temperatures. No, at these high temperatures and these low pressures. And the way we are doing this is we are using the HKF equation of state or the thermodynamic model together with a Diepau-Hackel simplified Diepau-Hackel activity model. And then within the superheated or supercritical region, we are using this new experimental data. I'm just going to show you how it looks like for what we are able to do. Of course, it's a first attempt, but it's very interesting. And for some of these gases, we have already some data, CO2 or H2S and so on. We have the thermodynamic formulation there, but we don't have it for the minor solids in most cases. And this is just an example of how this type of modeling looks like. I'm taking here basically a chemical closed system modeling from a liquid through the two-phase field of liquid and vapor to a single-phase vapor. Okay, and these are just the secondary minerals that are formed upon saturation, and this would be the evolved chemical composition and speciation in this type of a fluid. And this is just modeled using a very well-known HKF parameterization and activity model based on the Diepau-Hackel formulation. And you can kind of see things that you're having up on this boiling through this two-phase field. As an example here, you're having some minerals forming, their respective concentrations of the elements are decreasing and eventually maybe plunging down to zero eventually. In other cases, like with CO2, for example, or H2 or sulfide, the concentration seems to be relatively unaffected. It's just partitioning from the liquid phase to the vapor phase. So this would be for the total system in a way. And this type of modeling we have been carrying out, I don't know for how long, 40 years, maybe something like this. And there are many geochemical programs that are able to do such modeling. Chiller and GOT and Tough React, and we could go on and on, GEMS and so on. We heard some of these yesterday and this morning, or afternoon or evening, whatever you are, wherever you are. But then we add this new thermodynamic data that we're obtaining from the experiments together with the available data for some of these gases and so on, and this is what we get, kind of. And this is not a volcanic fluid. This is a supercritical fluid or superheated steam. Its calculations are done at 100 bars, and now we are just heating it up from 350 to 600 degrees and just calculating the equilibrium fluid composition and the possible mineralogy that could form. And of course, this is just an exercise. It may not have anything to do with reality, but this is trying to move forward in terms of breaking into a temperature and pressure field that we can't really have the modeling at the moment, so geochemical modeling. And here we can see that we are continuing seeing some of these simplified minerals, oxides, some silicates, sulfides, and so on. And here you can see the concentrations of the elements, for example. And what we were talking about here is, for example, that the CO2 that is sourced originally from this fluid, it's just continue heating up the subcritical water. The CO2 is basically unaffected. It's a mobile volatile component. The same is with H2S that is slowly converted to SO2 with increasing temperature. There is some HCl because most of the rock forming elements like sodium and potassium and calcium and magnesium, they have basically precipitated, and the leftover is a chlorine that forms an HCl. Silica actually has a solubility, we know that, and this is basically quartz solubility, and you can see that it's actually a little bit temperature dependent, but it's mostly pressure dependent. There are other volatiles like boron and so on that comes in, but most of the rock forming elements, they have concentrations that are just plunging down to approaching zero eventually. So in a summary, geochemical modeling of supercritical fluid chemistry is really limited, like Thomas was talking about previously, by thermodynamic formulation and thermodynamic data. It's not limited by the programs that are available. It's just the basics that are missing. And we have started doing experiments on simple solid solubilities in such fluids at elevated temperatures and low densities or low pressures. And we are not measuring some complex aluminum silicates or rocks or something. We're just starting with simple salts and sulfates and carbonates and oxides and so on. And there are almost no data available. We are slowly moving towards parameterization of these data into thermodynamic models. We are kind of moving ahead of what Thomas was talking about by just having some kind of a simple fit that we can introduce into some simplified calculations. But of course, this all needs to be revisited. But in order to start some simplified thermodynamic models of crossing into supercritical and super hot fluid chemistry from the supercritical thing. And of course, this is all very simplified because the data, the thermodynamic experimental data today, for example, are fitted assuming very simplified speciation model, ideal behavior, and you can go on and on and on. So there is still a long way to go, and there are no brines yet into anything that we have been doing, but we're making some progress. And I don't know if it will take us 5 years or 105 years to reach the eventually goal, but the progress is already being made in terms of some of these thermodynamic models that Thomas was talking about, experimental data that can be implemented into such models to parameterize them, and then just doing some simplified thermodynamic modeling of this supercritical fluid chemistry. So I think I'm going to stop here.
Thanks a lot, Andri. That's really, really interesting to see all of this new experimental work that is going on. There's a question around the thermodynamic of supercritical fluid and the possible similarity with deep sea hydrothermal vents. Do you have any comments on that? Is there some similarity between what you're doing and some deep sea hydrothermal vents?
Yeah, Yeah, of course. So I, so,
Of course.
yeah. So I guess the next thing that we need to start doing is kind of benchmarking our calculation towards some data and data that we have on fluid properties and alteration mineralogy mostly come from porphyry ore deposits. Definitely. Yeah.
So that's really linking very nicely with the question.
Yeah. It has to go there because we don't have a lot of data from active geothermal systems.
Well, no, we haven't. Yeah, that's for
There are
sure.
some, but it's mostly from the fossil ore deposit systems.
Yeah. So and then you're like there is some equivalent also in active, not only active but deep drilling as well in volcanic environments that are not, we are not target for supercritical resources, but more for volcanic that are useful. I'm not thinking like for us is the drilling in the Camedex, for example, that was it's a big insight as well. But
absolutely, and we are also trying to benchmark some of this against just volcanic gas data. Okay. Yeah. Just simple fumarole type data in a way. And alteration mineralogy or geolic type alteration mineralogy. Yeah, but we have been so soaked in trying to get all these experiments running and just making the models not crashing that we haven't yet somehow started to look into reality. But maybe in a few years' time.
Yeah. I guess, I mean, to link with the question with Pat here, that if we can use some geochemical information from porphyry copper, which we already answer, like alteration mineral assemblage and information from the fluid inclusion to compare with the experimental work, I'm guessing I mean, and Thomas will know as well, because working as well in porphyry copper environment, they must have run into exactly the same issue with modeling and thermodynamic limitation in trying to understand the mechanism of deposition and fluid dynamic around porphyry copper.
Definitely, so, but the limitations that we are kind of doing, we are all, me and Thomas and many other people within the GeoPro project, we are starting with almost pure water. Okay.
Yeah.
So of course this limits a lot of things in a way. Also in terms of comparing things to more salty systems or submarine vent systems or something like this. But we have to start somewhere. Okay, so we are starting with a simplified solvent in a way.
Yeah, I mean that's pure water, and then after like I mean obviously gas phases such as CO2 will is important to take into consideration. I'm guessing as soon as you're trying to incorporate some calcium system,
definitely,
like
and if you
things like that, that's exactly. Becoming
exactly. And if you have a binary system, water, CO2, water, sodium chloride, I mean, this would be another dimension in terms of these experiments. And if you have a ternary system, you can just see where this is going. It's just going to become crazy.
Is it the next stage of the development that what needs to happen?
Yeah, maybe, but then it also in a binary system, if you just think of that, you just also have to start thinking of partitioning between multi-fluids of elements and so on. So this is not trivial, and data for many of the systems, solutes in a binary system, it's just missing. Okay, we're just struggling even with the thermodynamics of the binary systems. So I don't know if this is maybe too much of a thermodynamics, but this is where we stand. And even for pure water, it's a data desert. There is nothing there. Okay, it's crazy.
Yeah. Well, it's for now, between all the work that is going on, you're slowly filling up the desert with data, which is great to see.
Yeah, we are quick.
Yeah. Thank you so much. Thank you so much, Andri, for those very interesting talks.